introduction, and then you can just carry on with your keynote address.
I'm ready.
Okay, fine, thank you.
So, did you want to say a few words before?
Yeah. I could do the introduction part of you before you proceed with your address.
Yes. It's a little, maybe a little before time, but that's perfectly fine with me.
Yes, sir. Yes. Just few seconds. Good afternoon, dear participants, and we'll begin the second session of Day 2 International Web Conference on Mathematics for Material Science, Signals, Images and Structured Data 2020 with eminent Professor Poul Hjorth, who was born in 1955, and he holds his doctoral degree in mathematical physics from University of California, San Diego. Since 1994, he has been Associate Professor at Technical University of Denmark, first at the Department of Mathematics and now currently at the Department of Applied Mathematics and Computer Science. And Professor has received the DTU Teaching Award in the year 2010. His research interests are in ordinary and partial differential equations, in particular with applications to industrial mathematics. He is currently Executive Director of the European Consortium of Industrial Mathematics, and his research visits to various institutes like Imperial College London and many more. And he has been a secretary and co-chair of the Danish Mathematical Society, and now is the editor of the Danish Mathematical Society newsletter. And also he is an editor at the Fields Institute journal Mathematics in Industry Case Studies. He is also Executive Director of European Consortium for Mathematics in Industry, and he is interested in the dissemination of mathematics in the culture of mathematics and mathematics in culture. In his research, he has touched a large range of subjects in mathematical physics, classical mechanics, dynamical systems, and geometry, in particular, and also in the applications of mathematics to real-world industrial problems. Organization of annual workshops between mathematics and industry, he is very much interested and he is doing it. The European study groups with industry in Denmark, he is doing with that thing. So may I now request our keynote speaker, Professor Poul sir, to proceed this platform and share your valuable things which you want to go and deliver to our conference. I welcome you, sir.
Okay, so let me see if this works. Yes. Can you see my screen?
Sir, you have not shared your screen. Try to share your screen.
Okay.
Yes.
It's coming.
Yeah.
Something is happening.
Yes. Your screen has been shared. Okay, sir.
And you see my cover slide?
Yes,
Excellent.
sir. Yes, sir.
So, wonderful. So, again, thank you for inviting me to this webinar. And I took a cue from the subjects that you had, in particular, signals, images, and structured data. And let me say that this will be a talk which is more philosophical and historical than technical. So I hope the students will forgive me, so they don't need to take so many notes. There will be some equations towards the end, but mostly, as I said, it will be philosophy. And I will talk.
Sir, excuse me, sorry to interrupt. And
Yes.
most of us are the faculty members, and very few are the students here in the meet.
Okay.
Okay, fine.
So here I will talk about the interplay between applied and pure mathematics, and this is an area where I have spent most of my life. And I want to relate to you some thoughts that I have about data and the way data influences both applied and pure mathematics. And for that, I want to reach back in history. And so the title of my talk refers to the Greek philosopher Plato and the famous allegory of the cave wall, which is several thousand years old, but it is still resonating with us. And I'm not a professional philosopher. Sometimes, mathematics is grouped with philosophy because mathematics by itself is not a natural science. So I won't go into the deep philosophical issues, but basically, if you know the setup or the metaphor, you see here in the slide, you see a prisoner who is chained to a wall, and the prisoner can only see images projected onto this cave wall of objects which are behind the wall, and there's a light, there's a fire that throws these images onto the wall. And the whole issue is, which is more real? Which is the real thing? Because the prisoner will never see the original objects, and Plato's philosophy had much to do with ideal and abstract objects, which we will never see, but we only see imperfect representations of them, which are the images on the cave wall. And you can apply this thinking to many things. In particular, you can apply to mathematics. And you can say the mathematical ideas that we have, are they images in our mind? Are they made by ourselves in our mind by staring at imperfect images, or do they have a presence beyond that? Do they exist? Does mathematics exist without human beings? Or you can phrase it differently: is mathematical things, are they invented by people, or are they always there, just waiting to be uncovered or discovered? And if you pose this question in a group of mathematicians, you will set off a long discussion. You better have a lot of time on your hands, because this will be a long discussion. And this is really not where I want to go. I will just say that my own personal attitude towards this is that the answer is probably somewhere in between, that it is a question which really does not have a yes or no answer. As you know, not all questions have a yes or a no answer. Let me give you an example. A mathematical statement like this is, of course, something that is patently true, and it is true, obviously, without anyone being there to work it out. You could even say it is the definition of the number 3, so it's almost a tautology. So there's no question that this is a universal statement which you can know or you cannot know, but it is certainly true without anyone being aware of it. On the other hand, a more sophisticated mathematical statement like this, which has a historical link to famous Indian mathematicians, is not so obvious, I would say. It has more the character of a construction. So these are two extremes of the question, and it is not clear, in my opinion, that you should answer the original question with either a yes or a no. But let me get back to data. And my field, as you heard in the introduction, is not data science per se, but I have a great respect for data, and I have a great respect for the influence of data on both pure and applied mathematics. And I want to talk today about an example of one of the world's first big data sets, which actually contributed to, and now you can choose whether you want to say discovery or creation of calculus, one of the most important breakthroughs late in the Renaissance. And the story I will tell is about the origins or one of the sources of this, and it has to do with a big data sets. So it is a real world data which has an influence on pure mathematics, and what later became the evolution of pure mathematics from calculus. And so in this metaphor of Plato, you have a direct interaction from the real or the perceived world back on the ideal or the Platonic world of pure mathematics. And it has to do with a different cave wall, not the philosophical cave wall, but the celestial sphere. The sky above us all, this dome that mankind has been staring at ever since the dawn of mankind itself. And if we go back 400 years, let me begin the story with a Danish nobleman called Tycho Brahe. Tycho Brahe was a nobleman, but he was also, because he was independently wealthy, he was able to pursue some interest, and Tycho's great interest was in observational astronomy. You would say he's the first very, very thorough observational astronomer at all. There have been earlier astronomers, but the whole art of careful observation began with this gentleman who was born in 1546. And as a young boy, we all know how you can be influenced as a young person by great events. And when he was 13 years old, he witnessed an eclipse of the sun. And it was not the phenomena in itself, which is also spectacular. I don't know how many of you have seen an eclipse of the sun, and I haven't myself, but it's supposed to be an awe-inspiring event. What inspired Tycho was the fact that it was predicted, that the hour of the day had been predicted. So this impressed the young boy with a strange feeling that the real power was in predicting things, that he wanted to be like. He wanted to be able to predict things and measure things in the sky. And then a second event occurred, which some people actually put down as one of the origins of modern science. And this was a November evening in the year 1572. And you can imagine in Scandinavia, in November 1572, there was not much light in the sky. And fortunately, on that evening, the sky was clear. It was a frosty night, and the stars were twinkling. And Tycho was on his way to dinner when he was stopped in the courtyard by some servants who were looking up into the sky. And Tycho said, "What are you all looking at?" And they said, "There's a new star." And Tycho was completely baffled because in the classical philosophy of the celestial sphere, stars do not come and go. The stars are eternal. And yet, when he looked up, he saw, indeed, they were right. There was a star in the constellation Cassiopeia, which should not have been there. But there it was, obviously for him to see, no matter what ancient philosophers had claimed about permanence of the celestial sphere, here was something new. And he started to measure it as best he could, and he quickly established that whatever light, whatever object was emitting this light was as much part of the celestial sphere as all the other stars. It was not something close to the Earth. It was as far away as all the other stars. And so, indeed, something has happened. There was a new star, and Tycho published. Even back then, you knew you had to rush into print with a new discovery, and he published a book called The New Star, and he became famous among European astronomers for his clarity and his observations and everything else. And he was also at the time in favor with the Danish king. That's a good thing to be with Renaissance kings, because they had so much power. I mean, the Renaissance kings ruled everything, and Tycho was a favorite scientist. And the Danish king Frederick II decided to boost his research, and he gave Tycho an entire island. It's a small island. I've been there, and it's an almost ideal spot to construct an observatory, because if you're on a small island with a high elevation in the middle, which this one has, you can have an observatory which has a complete clear horizon, 360 degrees all around. There are no mountains or forests that obscure the view. You have a perfect view of the hemisphere above you. And in addition to the island, there was a massive grant, which some people have worked out, and it corresponds to a few percent of the gross national product back then. And if you translate it into modern equivalents, it's an enormous research grant. I don't think there's ever been any research grant given with that magnitude. So he had almost entirely free hands to construct an observatory, a modern research center, and he did. So you see this in the middle frame. It's a later reconstruction from drawings, but we assume that his research center, called Uranienburg, must have looked something like this, and it was filled with instruments. Tycho had spent his early years perfecting the art of building large instruments. None of them involves optics, because these were years just prior to optical instruments. So there were no lenses and no glass involved, but these are large wooden and metal constructions with the best manufacturing that you could do in the day. And they had precision dials, and they had strings and levers, and they allowed you to make very precise eyeball and aided eyeball measurements of objects in the sky. And the whole discussion back then about the solar system involved actually three different views. To the left, to the far left, you see the classical view where Earth is centered and everything, as is the most immediate impression, it revolves around the Earth. In the center is the more modern view pioneered by Copernicus in 1543, where the sun is in the center and the Earth is but one of all the other planets, and you can see immediately it has the simplicity, it has pleasing geometric simplicity, but that doesn't mean that it should be right. And to the far right, you can see Tycho's own view of the situation, and it's very strange because in the center is the Earth again, and around the Earth you have the sun revolving, and around the sun you have all the other planets. And you may laugh, I can't hear you, but and it seems unnecessarily complicated. You can point out from a kinematical point of view that the Tychonian and the Copernican are actually equivalent. It's just a matter of where you put your reference frame. But Tycho actually had a very good reason to think that his model was the actual model, and that was because if the Copernican model was true and the Earth was actually in an orbit around the sun, he would expect some kind of parallax to show up. The parallax is the fact that if you shift your point of view, the line of sight to some faraway object will also change a little bit. But he could not measure this. And since he could not measure it as a true observational person, he was convinced that it actually didn't exist. And therefore he thought, no, the Earth is standing still. And then, of course, the sun has to go around the Earth, and he was perfectly fine with all the other planets going around the sun, and hence this construction. But he wasn't a great theoretical astronomer. His force was the measurements. And he drove in roughly 15 or 16 years a long, meticulous recording of the positions of the stars on the celestial sphere and the motion of the known planets around the stars on the celestial spheres. And there are volumes and volumes, and he made sure that everything was recorded, and of course with pen and paper, and he had a printing press, and it was printed. But it is the world's first big data set that he had there. Then in 1596, when things were humming along, something devastating happened, which can happen if you're at the grace of a Renaissance king. The old king died, and the new king hated Tycho. They quickly got into arguments, and it escalated, and Tycho was not an easy person to deal with. Apparently, he had a bad temper, and in the end, he was expelled from Denmark. And this is really bad for a nobleman to be expelled from his country. He went to Prague, where he was hired as imperial astronomer. And he took up service as imperial astronomer. It also involved a little bit of astrology. The two subjects were not particularly well separated back then. But he had this enormous data set. So he needed a computer. In the year 1600, Tycho acquired a computer to process his data. But this, of course, was long. This was about almost 400 years before the invention of the digital computer. So back then, computers were persons. So he hired a person to process his data. And he made a very good choice. He hired the German mathematician, Johannes Kepler, who was a young man at the age, and Johannes Kepler had made his fame in a very unusual way. So Kepler was a convinced Copernican. So Kepler, from aesthetic principles, the first time he saw the simple view, the Copernican view of the solar system, he knew that it had to be like this. But Kepler's thinking went further. So Kepler speculated, if you have the sun in the center and you have these spheres where the planets are moving, what is the construction? Because Kepler was also a religious man, and he was completely convinced that the solar system was built by God. And then he had to speculate, what is the design? Why are the radii of the spheres as they are? Today, we think this is a silly question to ask, but in Kepler's time, this was a deeply serious, this was the next step in understanding the solar system, was to figure out what is the rule, what is the principle behind these spheres, and in particular their radii. Kepler was hired at a boarding school for lazy boys, and he was teaching mathematics. And so one day in the year, it was apparently a hot summer day in the year 1597, Kepler was teaching geometry, and the boys were not so interested, and Kepler was not so interested in teaching. And then he did something that I think all mathematics teachers have done from time to time. He decided to give them a tough problem to work on, so he could be left in peace while they worked on it. And so he drew on the blackboard a circle, and he said, suppose this is a unit circle, a circle of unit radius. What is the side length of the triangle that inscribes it? And if you can work that out, you can probably also work out what is the radius of the circle that subscribes the or superscribes the triangle. If you have time left over, why don't you figure out the side length of the square that can be superscribed to the second sphere? And for some of the really clever ones, find the radius of the sphere, and so on. And so the boys started working, and he was left in peace, and he was looking at this drawing, and he was thinking to himself, by the way, the ratio of the orbits of the two innermost circles are almost in proportion to the radii of Earth and Mars, as far as he knew. It looked something like this, and so he was thinking, maybe the solar system is constructed in a manner sort of this, but then he thought, no, this is not going to work, because as you continue this construction, you will get higher and higher regular polygons, and they will approximate a circle more and more, and so the radii the difference in the radii will go to zero, and there's no natural way to end the sequence, and we need a construction which is perfect and harmonious. And by the way, in the real solar system, everything is in 3D, so you need to replace these regular n-gons with something that works in 3D. And then lightning struck. Then he had probably the single most brilliant idea of his career, because it occurred to him that in 3 dimensions, there's something very special about the number 5. Namely, you have 5 regular solids. So in whereas in 2 dimensions, you can have an infinite number of regular polygons. In 3D, the regular polyhedra are only 5 in number. This had been known since the ancient Greeks. So that if you do the equivalent construction in that he had just drawn on the blackboard, if you do this construction in 3D, you will have 6 spheres, because you begin with an inner sphere and you end with an outer sphere. And so this will naturally give rise to exactly 6 spheres. And there are 6 planets. So you may object here, but at Kepler's time, in Kepler's time, there were only 6 planets: Mercury, Venus, Mars, Mercury, Venus, Earth, Mars, Jupiter, and Saturn, and that was it. So he needed a construction that would give him exactly 6 spheres, and this was it. And he felt so deeply that he had suddenly peaked above the shoulder of God and seen why a deep truth about the solar system. And he, the only question is, what is the proper order of these 5? And then he took some cues from myth and astrology and symbolism classically associated with this, and it all worked out fine. And he was able to make a model of the solar system based on this principle. Here is the cover page from his publication in 1596 called the Cosmographic Mystery, where you can see that you have these spheres, and they, as spacers between the spheres, I use these regular polyhedra. This made him instantly famous as a young man, and physical models were made of this and presented to kings and princes. And so when Tycho Brahe was looking for a brilliant geometer and mathematician to help him make some sense of his big data set, Kepler was an obvious choice. And so Kepler went to Prague, and then Tycho died almost immediately afterwards in 1601. And Kepler, it's a long story here, Kepler made sure that he retained the large data set, because he knew that in this data set was the secret to an even more accurate understanding of the solar system. And he kept on working on that for the next almost 20 years, on and off, because there were other things in Kepler's lives. There were wars, there was diseases. Kepler's mother was accused of being a witch, so Kepler had to involve himself in lengthy court trials to keep his mother from being burned at the stake, and so on. It all took time, but on and off, he kept working on this data set. And in the end, he managed to extract 3 principles that seem to be governing the big data sets. And this is what textbooks today call Kepler's laws. I'm not so happy with the word laws. I would call them observations or principles or synthesis. First of all, they're not exactly true for everything we know, but they are guiding principles. They are very nearly true. So, and you may have seen them in textbooks. There are 3 in numbers. So from the left, there was the most amazing and surprising discovery that the orbits of the planets were not perfect circles. This was a complete break with antiquity, where you felt that for something to occur in the heavens, it had to have the perfection that only a circle or a sphere can have. But Tycho's data was so accurate that Kepler was able to determine that they were not spheres, that there was something slightly more ugly, namely an ellipse with the sun in one focal point. And in the middle, you see a kinematical observation that I will get back to. And at the far right, there's something about the size of the orbit and the period and observation that he could also extract. This is the fact that if you cube the major axis of each ellipse and divide it by the square of the period that the planet takes in evolving, you will get the same number for all planets. So there's clearly some kind of principle involved here that you have a constant, even if you change the size of the orbit, what is happening is that you also get a change of the period. So guided by this principle, and the middle law, sometimes called the area law, says that the area swept out in a given time, which today we would call dA by dt, but here Kepler just took it as a ratio of some small area under a small time, is constant throughout the orbit, and that means that the planet moves very slowly when it's far away, and it moves quickly when it's closer to the focal point where the sun is. So these things are called Kepler's laws. And following Kepler, 50 years after Kepler, things really took off when Isaac Newton wrote his famous textbook, probably the most famous textbook at all in mathematics, the Principia Mathematica. And as far as dynamical phenomena was, Newton, you could say Newton distilled phenomena into a super simple equation, namely this thing. It doesn't get much simpler than this. It's also a little bit obscuring, and everything has importance. So on the right-hand side, you have a new concept which Newton introduced and cleared up, namely, or to some extent cleared up, namely the forces that are acting. It's easy to understand what a force is. And on the left-hand side, P is the momentum, and the dot hides the secret of calculus. The dot is Newton's particular notation for a time derivative. So it's so tiny you can almost miss it, but it is actually the most important thing in this whole equation. And the point is that Newton's ideas were greatly supported and came very quickly into favor by the fact that all of Kepler's laws could be derived from that single force equation. And I will try to give you a hint of how that's done. So if you remember the area law, which I have at the top here, and I call, for cosmetic reasons, the constant not h but h/2. You will see in a second why I do this. So what is the area that is swept? If you consider during a small time interval, the orbit will, if you think in terms of polar coordinates, there will be a change in the angle d theta, and so I should have written r d theta for the segment out there. And so the area, the shaded area, is 1/2 times r d theta times r, and so you get 1/2 r squared d theta as the area segment. And if you divide both sides of this equation with dt, and since you all know calculus, you can immediately see that you will get a very compact equation called r squared theta dot is equal to h. And some of you who may know physics will recognize this as the constant of angular momentum for the planet, and that's exactly what it is. So this was the conservation of angular momentum that Kepler had discovered. And so if you take Kepler's laws, you would say from geometry, or this Newton was able to convert to find an acceleration of an object moving in with polar coordinates. So you have unit vectors, a radial unit vector ER, and you have a angular unit vector E theta. And if you work out what the acceleration is, this is just differentiating a couple of times. You'll get an expression like this. And now take Kepler's area law, as I've just shown you. Now, if you take the area law and you differentiate it one more time, you will find that it implies this equation. And now look at the top, and you will see that from the area law, there is no angular acceleration. All the acceleration is in the first term. So all acceleration is along the radius vector. And so Kepler's area law implies that that acceleration, that the planets are always accelerated towards the sun. And that means that the force is always towards the sun. So that's the law that's hiding inside the area law. And Kepler's ellipse law, here's the equation for an ellipse in polar coordinates. This implies, if you work it out, that the radial acceleration can be described like this. So the radial acceleration, the acceleration towards the sun, has a magnitude which is proportional to the inverse square of the distance. So you have a very simple explanation of why you have elliptical orbits, namely there's an acceleration or a force which is proportional to the inverse square of the distance. So it doesn't really get much simpler than this to explain why you have ellipses. And this was really Newton's ability to explain the elliptical orbits was really what propelled him to fame. And finally, the period law, used with the area law, which you can write like this, gives you an equation that looks like this, and you can rearrange it, and then you have this expression for the acceleration. So in the acceleration, the constant of proportionality is not a new constant of proportionality for each planet. It's a universal constant of proportionality. If you know physics, you will see that the constant c involves the mass of the sun and the gravitational constant, and that's it. So you can see the period law implies a universal force law that is not a new force law for each planet, but it is universal. And so Newton's law of gravity simply drops right out of Kepler's laws. I want to point out two things I find remarkable about this whole process, where Kepler has processed a big data set about planetary motion and discovered his three laws, which led Newton into fame and calculus into prominence. And that is the fact that, as I've said earlier, Tycho's original data set was so accurate. People have examined it now, and everybody agree that it takes naked eye observation to the absolute limit of what the human eye can detect of tiny changes in distant objects. It was so accurate that Kepler was actually able to uncover that the orbits were elliptical, because they are not very elliptical. I have greatly exaggerated the eccentricity of the orbits that I've shown you. If you were to see the actual orbits drawn on a piece of paper, you would probably not be able to see with your untrained eye that they were not circles. So the eccentricity is super small, but it is there, and it was there in Tycho's data set, and it is to Kepler's enormous credit that he didn't try to hide it, but he had so much faith in Tycho's observation that even though at first he thought it was ugly, he somehow, and this makes him a modern scientist, he felt the data says so it must be true. So this is the one remarkable thing. The other thing, which is not so often mentioned, is that, of course, in actual life, we know that the planets do not really go in perfect elliptical orbits. They wobble because they are being pulled and pushed by the other planets. And also, if we even include special relativity, we know that you have a precession of the perihelion. So they are not perfect and uniform ellipses, but Tycho's data was not so accurate that these deviations were detected. If they had been, Kepler would have gone mad. If Kepler had seen these wobbles and the perihelion precession, then he would have given up. and maybe calculus had been delayed for a long time. So we were very fortunate that this original data set had just these properties, that it was so accurate that eccentricities were clear, but it was not so accurate that all the secondary effects were visible. They were not. Today, mathematics and innovative data processing is more relevant than ever in history. And I gather, had I been given an hour to do this, moderator?
Yes, sir. Yes, sir. Till
So
1:30. Till 1:30 you've got time. 1:30
Okay.
you've got half an hour more to go.
So I will, yes, but I will carry on a little longer and take us rapidly to modern society. So even though I'm looking at my watch here,
Yes.
let me go on a little bit longer. And now I am putting on my hat of being director for the European Consortium for Mathematics in Industry.
Okay, sir. Okay, sir. You can go ahead.
Very briefly, ECME has a threefold mission to help in the education of industrial mathematicians, to promote modeling, simulation, and optimization, and basically to promote European collaboration in industrial mathematics in a wide sense. So it is not, membership of ECME is not exclusive to being a geographically placed in Europe. But let me get back to the importance of mathematics for society, because you have many independent reports that tell us that mathematics, not even for fundamental discoveries in physics and nature, but in a very real sense about the economy of a modern society relies very heavily on mathematics. These reports tell us that mathematics-related occupations continue to many of the jobs, if you think about it, and also since these jobs carry high salaries, the contribution to the national economy of nation states is even higher. And we know that mathematical skills in the workforce and mathematical innovation drives a competitive economy. That you can even make a correlation like this, where you can cook up some index of competitiveness, and don't ask me exactly how this is cooked up, but this is in the Dutch report from Deloitte. And on the x-axis, you have scores in mathematics in elementary and secondary school. And you can see that there's a very strong correlation that goes upward. So the more emphasis on mathematics, the more competitive a economy you have. And one final example I want to make is the contribution of mathematics to computational power. Often when we buy computers and we sell computers and we compare computers, we always think of the processing speed, and there's something called Moore's law, which has been in effect since, I think, all the way back into the 60s, that microprocessors double in power every so often years. It's the Moore's law. Every 2 years, the speed of transistors and microchips is doubled. So you're on a log plot, you will have almost a straight line going upwards, and it has been roughly true. And we may hit some kind of quantum limit, but it has been true for almost 70 years. So just in terms of raw processing power, the computers are getting more and more powerful. This is well known. What is not so well known is the power of mathematical algorithms, namely the software. And what is the surprising truth is that it also holds for mathematical techniques. So if you look at how much the contribution to processing speed comes from algorithms and software and mathematical constructions, it's even faster. As you can see, it's at least as rapid as Moore's law. And these effects, as the slide says, strengthen each other. And if we didn't have this continual evolvement of software and algorithms, someone pointed out that we would be running computers now with the speed that they had in the 90s. But we don't. We have massively speed, but at least half of that progress has been made by pure mathematics and computational techniques. So this is definitely a food for thoughts, linear, mixed integer programming. And here's a slide that shows you how the progress has been made. So continuously we are getting better and better at programming the computers so that they can take advantage of the microchip evolution. So we are continuing to ask each other what's going on. We have big data, and we need innovative mathematical techniques. I can mention topological data analysis and many other complicated things, and that will be a separate talk. But I think hand in hand with just staring at the data and processing the data, we need to be thinking. Like Kepler, we need to have the human mind in play also, because it is a unique ability of the human mind to get insight into the phenomena that we are looking at. So it's a balance between these two pictures, where on the one side you're looking just at data, and the other side you're looking at phenomenological models and causal phenomena, some of which may have stochastic elements, but still we are getting better and better at doing this. And this is my second rapid, so I think I should stop now and maybe leave a few minutes for questions. So that's the end of my talk.
Thank you so much, sir. And dear participants, the queries which you have got, you can just clarify with the professor.
If there are any. It doesn't seem to be the case, or people are shy. And you can find my email and you can write to me. Maybe this is not the ideal forum for an exchange of questions.
Yes, sure, sir. Thank you, sir. I could say it was a brilliant session. We had you in our conference. Really an excellent and fantabulous speech you've given here. We are very lucky to have you amongst us. Model of solar.
I was happy to be there. Thank you very much.
Yes, sir. Yes, sir. We could say that today is a day that we had a privilege to know the origin of data set, so-called Kepler's observation, as you have rightly pointed it out. So
that was the idea. Yes.
Yes.
Okay, I will stop presenting now.
Yes, sir. Thank you so much, sir. See you
in
the near future. Thank you so much. And dear participants, college children, sir.
Ma'am? Yes, ma'am.
Shall we have a lunch break here?
Yes, ma'am. Yes, ma'am.
At what time we all can join again?
Maybe 1:40.
Yes. So dear participants, we all can break for the lunch